and we have the guiding camera that will observe the guiding field of view, the field of view of the telescope. And the idea, if I remove some parts here, I just see that the system is that we send the telescope light towards the hole, which is in this small mirror, and we have this reflection system to the guiding camera to see the field of view of the telescope, and all the light that is going through the hole of 50 micron hole in the mirror is sent with another optics below the mirror, is focused on the fiber, and this is where we have to align very precisely the hole and the fiber, and this is done by these screws here. But this is a very precise tuning. Okay, and as a result, the guiding image with the guiding unit is something like that. So you don't see anymore a slit, but you see a hole in the middle of the image, and then you can see exactly where which star you are pointing. Or in this case, you can imagine that if you put your hole here or here or here on the moon, of course, you'll not have the same result, and you can start working on the physics of the moon. Okay, and also very quickly, with the eShell, you also have a calibration module. We didn't talk about the calibration light, but this is very important to understand that mechanically speaking, optically speaking, we don't have enough precision to be sure that to ensure that these wavelengths will arrive exactly on this pixel on the camera. This is too much precise, and there are mechanical gaps and tolerances and so on, and on the optics also, and it's absolutely impossible to do it. So if we want to calibrate our spectra, we just have to use some calibration light, and calibration light means a light for which we have some emissions at very well-known wavelengths, and we inject this light in the same condition as the light coming from the star, and then we do a spectrum of this, and on this spectrum we are able to recognize a pattern of light, of line or some few lines, and then based on that we are able to establish a calibration law, a dispersion law of the light on the sensor. Okay, but this is really to be done at almost each observation. As soon as you change anything in the telescope, if you remove the camera, if you change the fiber or something like that, you do have to redo the calibration. Okay. For the eShell, we have a lamp, a thorium argon lamp, which is an holocathode lamp used at quite high voltage. So I think it is 200 or 250 volts. Oops, sorry. No, sorry. Here, right? And this lamp, the thorium argon spot is just the small blue part here. And in fact, inside the calibration module, we have some optics again to transport this spot in the middle to the fiber. Okay, and we also have some flat lamp on the side, and we can also inject some flat lamp and in the guiding unit. Again, and we use another fiber, which is the calibration fiber optics, that is sent to the guiding unit, and you have here the connector for the calibration lamp at this position. Okay, and the interest of using a thorium lamp is shown in this image. This is a calibration image with the eShell spectroscope, and you can see that in each line, each order, you have many emission lines, and we can know exactly the exact position of each line, and this is what allows to do such a calibration. So the advantage of the thorium is that we have a lot of lines with quite similar levels, and except the very bright at the top, and oh, sorry again. And here, And this is when I move the mouse too fast. I'm sorry. And so you have a lot of lines that allow to make a very good dispersion low. With any other lamps, you are you still there? Oh, I missed you. I have to wait. Are you still around? Oui.
Oui, François.
Ça a coupé.
Allô?
Oui, j'entends.
Oui, le système qui a planté, donc on reboot.
D'accord. OK. Ben, moi, je suis toujours connecté. J'attends que vous vous reconnectiez. Ça marche.
Ça va dans 5 minutes. Merci beaucoup.
D'accord,
Désolé.
pas de problème.
Can you hear us? François?
Oui.
Oh, sorry, we have a technical issue, so you can resume.
Okay, wonderful. Okay, perfect. Can you tell me quickly where I've been stopped? Or do I continue?
The slide before this one.
Yeah.
Okay, we're here. Okay, so I was just saying, tell me if this is okay. I was just saying that the thorium argon lamp has the advantage of many lines in each order of initial spectrum, and then if you would use another lamp than thorium argon, and especially thorium, then you would see only a few lines per order, and it would mean that it would not be enough to do the calibration. Okay, and just to try to give you the direction for the next step is that above the E shell, we also have the whoop shell instrument, which is a big instrument because this is a 2 meter long instrument. And the principle is the same. So this is again an E shell spectroscope. with many orders, but we have a much higher resolution, which is roughly 30K instead of 10K for the E-shell. Again, this is a much more complex instrument, and we have a white pupil architecture. Well, it would be interesting to spend some time on that, but I'm afraid we don't have the time right now. But this is just a great architecture, and that gives this kind of image. Well, you can compare. It is quite similar to your E-shell calibration image, but we have more orders and more details in each order. Okay. Well, I've finished with the spectroscope itself, and very quickly we'll go to the main parameters. So the next sections are shorter, so I think I will be on time at the end. Well, I've already talked about the resolution and the dispersion, wavelength domain also a little bit, and I will spend more time on the F ratio and the slit size and the camera sampling. Okay, so this is very quickly about the resolution and dispersion. I've already shown this image. I just want to give you this other example where I've written the word celiac with the mouse, which is not easy to write with a mouse, but in a way I've taken this pattern here and I've copied it here. I've just changed the width of the line. And in one case, you can read the word. In the other case, you cannot absolutely not read the word. However, this is exactly the same information that is 2 times in this image. And then when you are defining the resolution you need, think about the magnitude, think about the resolution and the details you need to see in your spectrum, and also think about the exposure time, which is the critical thing when we want to do some surveys, for instance. You know that spending 1 minute or 1 hour on each of the target is absolutely not the same thing. Regarding the wavelength domain, I already talked about that. This is also, of course, a major parameter of the spectroscope. So can you go what is the bandwidth that you can cover, and also can you go very far in the blue? Can you go far in the red, or even in the infrared? And then usually when you have a low resolution spectroscope, you cannot change the grating angle, generally speaking, but for the high resolution, you have a system that allows to select which part of the visible spectrum you will observe. So think about that when you select an instrument, of course. And now regarding the F ratio or the aperture matching between the telescope and the spectroscope. So I hope that it will partially answer your question, Abdelmajid, at the beginning. So you know that the normal situation is this one. You have what we call the F ratio, or FD, focal diameter ratio. This is the division of the diameter or the focal length by the diameter of the telescope. Again, so I do consider that a telescope is a single lens. As a first approximation, it is correct. And of course, this angle you have here, the angle of the beam here, must be the same in the spectroscope to be sure that we catch all the photons. Okay, and this is the beginning of the spectroscope. You recognize the collimator lens, you recognize the dispersing element, and so on. Okay, so this is the perfect law. Now, what happens very often, is something like that. You have, for instance, a Newton telescope, a Newtonian telescope, which is at f4, for instance, and you have a spectroscope which is f7. In this case, what happens? You'll see that this light, this part of the beam with the gray area here, will not go into the spectroscope, and this light will be lost, in fact. And then you will lose light by vignetting. So it means that this light will never enter in the spectroscope. And if you look at this image, it would be exactly the same if you would have a smaller telescope. If the telescope has this diameter, you would have something that will not lose any light, you know. But in this case, you have a big telescope and you will have exactly the same result as if you had a smaller telescope, which is a pity, of course, because a big telescope is something very expensive. So it's important to match both configuration. Now think about the other situation, the reverse. You take, for instance, a Ritchey-Chrétien telescope at f8, and you have an LP spectroscope that can go down to f5 or even f4. You will be in this situation. So in fact, the spectroscope is bigger, and then the light beam is smaller. So in this case, the good news is that you are not losing any light. So the 100% of the light coming from the telescope will go into the spectroscope. Okay, and we can say, okay, it's much better than the case before. Yes, but in fact, there is another problem, which is you are not using the whole capability of the spectroscope. In the previous cases, you were not using the whole capability of the telescope. Now this is the capability of the spectroscope. And the result is, if you would put a focal reducer here, then you could shorten the focal length of the telescope, and then you would reduce the size of the slit. And you would be able, in fact, by doing that, you would have a smaller star image, and then you could, with the same resolution, you could, with the same telescope, you could close the slit in order to improve the resolution, you know, just by shortening this focal length. And this is a pity not to do it, because in this case, you will have you will lose some light either by vignetting at the slit itself, because the star image will be bigger than the slit, or you will lose some resolution capability. So in any case, it's always better to be in this situation and to make to do the best to have a good matching. Now, you know, it's never perfect. It's very, very currently, even on big instruments, the matching is not 100% perfect. And usually, if you want to have it, you have to design your own instrument to make sure that it perfectly fits your telescope. So it's, of course, this is very, very expensive. So we can accept that this is not perfect, but we have to keep that in mind to be sure that we are doing something serious. Now, regarding the slit size, we already talked about that, but imagine that with a small telescope of 20 centimeters like this at f10, which is a Schmidt-Cassegrain telescope, very basic, the image of the star is roughly, well, depending on the seeing here, it is something. Oops, sorry again. It is something like 20 microns wide. And if you have a bigger telescope, a 60 centimeter telescope with the same slit, you see that in this case you will lose light, and it will be even worse with a bigger telescope, with a 2-meter telescope. So really, you have to adapt the slit on one side to the spectroscope resolution and the pixel sampling, but on the other side, you have to adapt the slit to the telescope. Okay. Regarding the seeing and the star image size at the focal plane, keep in mind that the star image size depends only on two parameters. The first one is the seeing, which is in fact the angle from which you do see the star from your observatory, from your telescope. And this is the star by itself is really like a point, and you cannot have any resolution, you cannot see any detail of the star, but the atmosphere makes perhaps some vibration, and then it will spread out the light and it will give this angle. So the seeing angle is really a specification of the sky and not of the star behind it. The star, we can consider it is perfect, but the sky, the star is perfect, the sky is not. Okay, and the second parameter is the focal length. So for a given seeing, if you double the focal length of your telescopes, if you have a telescope twice the time, then the image will be twice the time. Okay, this is linear. So again, this is why it's so important to consider that if you increase the size of the telescope, you will have to increase the size of the slit and then of the spectroscope for the same resolution. Regarding the camera sampling, this is also something very basic but so important. The optical system is able to do something like that. It can be a star or it can be an emission line in a spectroscope. The principle is exactly the same. The idea is that you should have a correct sampling. So ideally, this pattern should be covered by few pixels. So in theory, it is at least 2 pixels. In practice, it is better to have 3 to 5 pixels. Okay, so you should have something like that. And so in this case, you will have all the information that is contained in this shape. If we consider that this is a Gaussian curve, in fact, a Gaussian curve is defined by 3 parameters, which is roughly the average position, the central position, the width of the width of the shape, and the intensity of the star. So only 3 parameters are enough. And if you are doing such a sampling, you will be able to catch all these 3 parameters with a quite good precision. If you are 2 small pixels compared to that, you can say, hey, I will have much more details, so I will be much more precise. In fact, this is not true because all the information is already contained in this. And on top of that, you can understand that if the pixel size are smaller, then each pixel will receive much less light, much less photons than in this case. And then you will be much less sensitive, and you will have to have a much longer exposure just to have the same signal to noise ratio. And at the end, you will not have any any other information than in this case. So it's a pity. The other extreme is the subsampling. If the pixels are too big, then you will lose information. So in this case, you will not be able to tell exactly where is the average, the central position of the line. Okay, you will lose this information because of the subsampling. So in this case, in fact, you have an optical system that is able to give this precision, and you will lose the precision because of the camera. In this case, this is the camera that will give you the limit, the limit of the performance of your system, which is a pity because usually this is the optics that is the more complex. Okay, so the question of sampling is something important. And again, remember that the spectrum is a multiple image of the slit, and then really this is you have to consider that this is the slit image on the CCD that will give you this size. Okay, so the correct sampling is that when you project the slit image to the sensor, it must cover a few pixels. Again, this is ideally. In the real life, it's not always possible. And so I covered these main parameters, and now a few recommendations to finish about the observation in the field that are very important when you are observing for real. The first is the focusing order. If you have understand the schematics, so we have the telescope, which I can consider as a simple lens. Sorry, you have. Oops, this is this one. You have the spectroscope. Here I do have only the collimator lens at the beginning of the spectro, and you have the guiding image system that is able to look at the telescope field of view by transporting the image at the focal plane. Okay, so it means that you have 3 optic systems that must be focused on the slit. So really the slit is the center of the world. And the idea is really to do that. First, you can, and independently, you can focus the spectro in order to have sharp images of the slit, which means sharp emission lines, for instance, if you are using some calibration line. So very often we use calibration lights at the input, and we focus the spectroscope in order to have sharp lines. So this one is easy. Now, the most critical here is that you have then to focus the guiding camera. And to do that, you can do that during daylight, and just make sure that the slit image is very sharp in the middle of the image. Okay, so the slit must be sharp. And once you have done that, after that, you can focus your telescope in order to have sharp star images in the field, in the guiding camera. Okay, if you do that in the other way, so if you forget to focus properly the guiding camera on the slit, and you just do the focusing of the telescope, in this case, you will have sharp images of the stars, but it will not be optimal at all because you will be in this situation. So in this situation, the slit is here and you have focused the spectroscope to the slit, but in fact, the telescope is focusing at another plane. And if you do that with this way, you will see sharp star images in your guiding image, but the slit itself will not be sharp. And then in the focal plane of at the entrance of the spectroscope, which is the slit, the image, the star image will be very wide. And in this case, you will lose a lot of light. And again, this is a pity because you just have to focus in the proper order. So be very careful because this is a very common trick, just to forget to see properly the sharp slit. And by the way, a very good way to check that this works perfectly, it is that when it is well focused, when the star crosses the slit or the fiber for the eshell, you will see the star disappearing in the image. If you are in this case where you are not properly focused, you will see that in the slit you have only few percent of the light that is going through the slit, and then in your guiding image you don't see the star disappearing in the slit. Okay, so this is really a very important criterion. Okay, well, you have this just for kidding. I like to use this picture saying, while pointing at a star today, it's not difficult to have, I have a go-to mount and I just have to ask my computer to point the telescope to the right star. The problem is that when you look at the sky, we have many stars. So I think this is Deneb, if I'm right, in the Cygnus constellation. All the other stars cannot be seen by a naked eye. And one day we just asked people to observe this star, and here you say, okay, maybe we have a problem to be sure that this is this star that I will put in the slit. So do consider that it's not so easy to point at the right star because you have mechanical fluctuations, because you have the atmospheric refraction that moves a little bit the stars in the sky, because you have mount alignment errors. Again, this is never perfect. And all these things makes that when you ask your telescope to point exactly at what star, maybe it will be close to the slit, but it will be almost never inside the slit. So you have to make something to make sure that you are putting the star in the slit. Okay, and by the way, it's important to check the sky map that you recognize the pattern. You are putting the right star in the field of view, and you have to calculate your guiding field of view to put that on the sky map and recognize the pattern of stars. And when you used to do it, it's quite easy, but at the beginning, I know it's something which can be frightening. And by the way, also, today we have the plate solving tool. So the astrometry.net system, that is how you just send an image with the pattern of stars, and the system is able to recognize the pattern, and it is able to say the center of your image is exactly at these coordinates. So it's really changed our lives, but it is important to use that. And in any case, make sure that you are pointing at the right star. Okay. And just to finish, it is important also for me that to understand that I talked about the instrument, the structure of the instrument, the dimensioning of the instrument, and so on. But once you have made your choice, when you have selected the telescope, the spectroscope, when we have attached everything together, we have selected the camera and so on, during the night, you don't have a lot of parameters to play with. But your mission during the night, during the observing session is finally very simple. You have to point at the right star. And I insist on this point, but I know a lot of very experienced observers that just missed at least one time and say, oops, it was not the right star. Usually you discover that because the spectrum is absolutely not the spectrum that you did expect. But I know you I do consider that an experienced observer has already made this mistake. At least once in his life. And most important is that you have to put as much light as possible in the slit. Really, the difference between a poor observation and a good observation is that the difference will be in the signal to noise ratio at the end for a given exposure time. So it means that you must put all the possible photons in the slit. So take care of the telescope focusing, take care of the tracking parameters, to make sure that the star is not moving, evolving, vibrating around the slit, and make sure also that the target position is really in the middle of the slit and not a few pixels aside. We could say, well, I'm not far, so it should be enough. And in fact, maybe you are losing 80% of the light, and this is a pity. Okay, and well, that's it. All the other element depends on the instrument. And finally, also keep in mind that the telescope and the spectroscope are just some acquisition devices to fulfill the reduction process. So I'll not talk about the reduction process today, but this is a very important part in the observation. And really, if you consider that I will do the acquisition and then I will try to process my data, I think this is a mistake. You have to understand how it works, the data processing system, how to reduce your data, to process your data. And then when you have done that, you can start creating your own image that will fulfill this process. And if you process this way, the thing, your life will be really easy. In the other way, you will be much less efficient in your observations. Okay, so this is just, you already showed earlier the book. I do have written this book a few years ago, and we have the English version and the French version. So maybe just after this meeting, we can organize some signature session. I'm kidding. I'm sorry to not be with you. I would have preferred to be with you, but that's life. One day I'll be with you. And anyway, in this book, I've put many things that I've described today. And this is really a lot of advices for beginners in spectroscopy. And that's it. And I've finished. And I'm now ready for some questions if you have. And any case, thank you very much for your attention.
Thank you very much. Any questions, please? Okay.
So either I was very, very clear, or I was totally out of topic.
No, it was fine. It was clear.
Yeah, so we can get the book.
Yeah, so
I got a script of online version.
You were spectroscopy.
Well, our question. So someone asked if we can get the book online.
On PDF.
Online version?
Yes, yes, yes. Well, yes, you can buy the book at the Sheliak website, yes, or even on any. I'm sure that you have some book resellers close to you, and it is available very widely, even on Amazon.
Okay, is there the difference between the resolving bar and the resolution bar?
A difference between, sorry, I did not understand. A difference between resolution and?
resolving power and resolution power.
Resolving power,
And resolution power.
is there some difference?
Okay, between the resolution and the resolution power, right?
Resolving power.
Resolving power.
Yeah. Pouvoir de résolution.
Slide 30.
No, okay, so well, resolving power and resolution power, this is the same. So I think that the right wording is resolving power. I think maybe I made a mistake in the presentation. Anyway, the resolving power is a figure without any unit that gives, this is in fact the lambda divided by delta lambda, and delta lambda is the smallest detail that you can see in your spectrum. Okay, so this is the resolution power. The resolution itself is the smallest detail that you can see in your spectrum.
Thank you.
Just one question about young astronomer. What is the concept to get them to beginning the spectroscopy? Because we have a new community of astronomers, young astronomers, and if you want to begin spectroscopy, which material, which telescope, which spectrograph can we in the beginning? Thank you.
Well, so this is a very open question. If you want to start in spectroscopy, I think the most important is start with what you already have. If you already have a telescope, I think it's better to use this telescope instead of saying, well, I have to have a new telescope, a new mount, and anything. So the simplest is the best, and start with what you have. Even if it is not optimized, this is not a big deal. Maybe you will not be able to catch faint targets, but you will start observing, and this is by starting observing that you will acquire experience. So now, if you have the choice, so if you don't have any equipment, and you do have the choice, well, it really depends. If you have one program in mind, if you say, for instance, I want to observe all the different spectrum classes of stars, or if I want to observe, to measure the Doppler shift, the redshift of the galaxies, or things like that. If I want to observe the B stars or earlier A stars and so on, in this case, you can say, okay, so if I know that, I know the resolution I need, and then I know the kind of exposure time I need, and then starting from that, you can have an idea of the dimensioning of your instrument. But if you don't have any idea, if you just say, well, I want to start in spectroscopy, I'm a beginner, I just want to discover, in that case, my recommendation is to start with the low resolution, because with the low resolution, this is like in photo, you will have a wide angle instrument, and you will be able to see all the differences, all the phenomenon that you can find in the sky. Okay, the spectrum of the star, of different stars, or a galaxy, or planetary nebulae, or any kind of object, of comets or planets or things like that. They are all different, and this is you'll much better understand and see the differences with the low resolution. And in my mind, low resolution in our product range. So I'm not trying to sell you our instruments, but in our product range, I mean the LP 600 is really the easy instrument to start with in spectroscopy. Now, regarding the telescope, to start with, we don't care about the diameter of the telescope. Even with a smaller instruments, you can really do a very, very good things. And this is always a pleasure to use the existing instrument. And really, in fact, the quality of your measurements will not depend on the diameter of the telescope, but it will depend on your own methodology that you'll use during the observation. So and with a small instrument, everything is smaller. It is easier because everything is smaller. So the mount is smaller, the tuning is smaller. If you have to move to take your instrument in vacation or things like that, everything is easier. So you can start with a small instrument. Now, I do have one recommendation. If you want to buy one telescope to do spectroscopy, in this case, my recommendation is to use a purely mirror telescope. And in order to prevent any chromatism effect due to any glass element in the optical path. And purely mirror telescopes means mainly the Newtonian telescopes, which are simple, cheap, and easy, and they are fast telescopes, usually f5, f4, or even f3. And the other very common architecture is the Ritchey-Chrétien, which is also a purely mirror telescope. All the Ritchey-Chrétiens are at f8. Almost. I think I've never seen Ritchey-Chrétien at another f ratio than 8, and which is great for the highest resolution. And these two architecture has no chromatism by construction. And when we are using instruments like the LP, the UVEX now, and this kind of instrument, we can go very far in the blue part and in the red or infrared part of the spectrum. And this is very useful in this case to avoid any chromatism in the telescope.
Okay.
Yes.
We have one question, please.
Yes. Okay. So, for the star image or profile, you said it has the correct sampling, which means the star spread over 3 or to 5 pixels.
Yep.
And in case if there is oversampling, so we can do binning to have the right sampling. But if it's undersampling, how can we correct for that? Is there a correction for that?
That's a good point. No, there is no correction, and you must adapt the optics. So you're right. If you are oversampling, you can do some binning, and then you will collect all the light from different pixels in one single pixel. So you will artificially extend the size of the pixel, so you can adapt the sampling. But in the other direction, there is no way, and you just have to maybe to increase the slit and but in fact, in practice, in real life, I think this really never happens, especially because today, that we are switching from CCD cameras to CMOS cameras, and the CMOS cameras has smaller pixels than the CCD. So today we are facing, usually facing the problem of oversampling. And in fact, when we have seen some problems or subsampling or undersampling, it was when people used some binning and it was a mistake, okay? Because the advantage of binning, of using the binning in your camera, is that your camera is more sensitive. So if you are observing faint targets, you may have the temptation to do binning to collect more light and to be more sensitive, and it will work. But you have to really check that you are not binning too much in order to keep the right sampling.
Okay. Is there another question? No? No? Okay. So if you don't have any question more, I will thank on behalf of all the organizers and all students, Monsieur François Couchard, qui nous a fait le plaisir d'accepter l'intervention très, très, très riche. Donc, au nom de tous les étudiants divers pays, donc on a l'Afrique, le Nigeria, on a du Sénégal, du Qatar, des Émirats, on a aussi même de France. Et donc, voilà, je vous remercie au nom de tout le monde et à bientôt.
Merci beaucoup. Merci. Bonnes observations. Merci de votre assistance.